This is Lesson 6, Exact Ordinary Differential Equations by Ronald Johns. We will see how to recognize exact equations and how to solve them. To understand exact ordinary differential equations, we have to understand partial derivatives. So let's quickly review partial derivatives. Suppose we have a function of two variables, f of x and y. We can talk about the partial derivative of f with respect to x, and it's denoted by this symbol, the partial derivative of f with respect to x, and we're evaluating it at some point x and y, let's say in the Cartesian plane. It's defined to equal the limit as h goes to 0 of f of x plus h, comma y, minus f of xy over h. When we look at this definition, we notice that the second coordinate remains fixed, constant. Y remains constant in both of these terms. The first value here is x plus h, and over here it's x. So what we're doing here is looking at the rate of change of f in the positive x direction. To find the partial derivative of f with respect to x, we'll think of y as being held constant or unchanging and consider f to be a function of x alone and differentiate it, as in Calculus 1, as if it were just a function of one variable. So let's look at an example of finding the partial of f with respect to x. Let's let f of xy equal sine of x squared y. Let's find the partial derivative of f with respect to x at the point xy. So in other words, we want to find the partial derivative with respect to x of sine of x squared y. Well, if we think of y as being a constant, then we would differentiate this exactly the same way as this Calc 1 problem, the derivative with respect to x of sine of a constant times x squared. That's equal to the cosine of that constant times x squared times the derivative with respect to x of that constant times x squared. So cosine of a constant times x squared in this case is cosine of x squared y. The derivative with respect to x of that constant times x squared in our case is the partial derivative with respect to x of x squared y, where we are treating y as a constant. Up here, this derivative would be 2cx, and down here it would be 2yx, which is the same as 2xy. So everything that we did here was treating y as a constant, but we had to use partial derivatives here to remind us that we're taking partial derivatives of a two-variable function. So now let's consider the partial derivative of f with respect to y at a point xy. Let's continue our example. Let's let f of xy equal sine of x squared y, and let's find the derivative of f with respect to y at xy. So in our solution, to find the partial derivative of f with respect to y, think of x as being held constant and consider f to be a function of y alone, and once again differentiate as you do in Calculus 1. But in this case, since we have x squared y, what do we do with this x squared? Well, if x is considered a constant, then x squared is also a constant. For example, 5 is a constant. 5 squared, which is 25, is also a constant. So when we take the partial derivative with respect to y of sine of x squared y, we're going to treat the x squared like a constant. And so we're just differentiating here sine of a constant times y, sine of cy. Well, in Calc 1, you found by the chain rule that's cosine of cy times the derivative with respect to y of cy. So down here in our two-variable case, this partial derivative is going to be the cosine of x squared y, this is c times y basically, times the partial derivative with respect to y of x squared y. And now, the partial derivative with respect to x squared y, with respect to y, is just x squared. And so we finally get the answer x squared cosine x squared y. Let's look at the second partial derivative of f with respect to y and x, evaluated at the point x, y. By definition, this second partial derivative of f with respect to y and x, evaluated at x, y, is the partial derivative with respect to y of the partial derivative of f with respect to x, evaluated at x, y. For example, let's let f of xy equal sine of x squared y. Let's find this second partial derivative. Well, in that case, the second partial derivative of sine of x squared y with respect to y and x, by definition, is the partial derivative with respect to y of the partial derivative with respect to x of sine of x squared y. We already evaluated this partial derivative with respect to x of this particular function earlier, and we found it to be 2xy cosine x squared y. So what we have to do next is to find the partial derivative with respect to y of this stuff. Well, this stuff happens to be a function of y times another function of y. So we have to use the product rule. So we'll take the derivative of this first function of y, which is 2x, times the second function, which is cosine of x squared y, plus the first function, first factor, 2xy, times the derivative with respect to y of cosine x squared y, which is right here. Okay, well, this one we've already evaluated. Now, in this term over here, we need to evaluate this partial derivative with respect to y of this stuff. Well, once again, let's use what we know about taking partial derivatives with respect to y. We'll treat x like a constant, and thus we'll treat x squared like a constant. So we differentiate this as we would differentiate the cosine of a constant times y. And so that's going to be minus sine of x squared y times the derivative, partial derivative with respect to y of this inside stuff, which is just x squared. This term can be algebraically simplified somewhat. I'll leave that to the viewer. Here's a result that we'll need a little bit later. It's called Clairaut's theorem. If the second partial of f with respect to y and x at xy, and the second partial of f with respect to x and y at xy are both continuous in a region containing the point AB, then these two mixed partial derivatives are equal at the point AB. Notice that we are reversing the order of differentiation. Here we're differentiating with respect to y, and then inside with respect to x, and here they are switched. So under pretty mild conditions, we have that these mixed partial derivatives will be equal. Here is a chain rule involving partial derivatives. Let's suppose that z is a function of x and y, so z is f of xy. Let's suppose that x is a function of the variable t, and y is also a function of the variable t. Then we can consider z to be a function of t, and here's how we can find the derivative of z with respect to t. The derivative of z with respect to t equals the partial derivative of f with respect to x times the derivative of x with respect to t, plus the partial derivative of f with respect to y times the derivative of y with respect to t. Now let's look at this a little bit more carefully. We're thinking of z as a function of just one variable t here, and so this is the ordinary Calc 1 derivative of a function of one variable. X is a function of one variable t, and y is also a function of one variable t. So in this formula, we have ordinary derivatives with respect to that variable t. F, on the other hand, is a function of x and y. So when we talk about the derivative of f with respect to x, that is a partial derivative. Also here, we have the partial derivative of f with respect to y. We are going to need to apply this chain rule to a particular problem. And the problem is this one. Suppose the equation capital F of xy equals c defines y as a function of x implicitly. What differential equation does excuse me, y of x satisfy? So let's see what we can do with that. So if y of x is a solution to this equation up here, that means that capital F of x comma y of x equals this constant c for all x in some interval. Well, in this function, x is a function of x, and y is a function of x also. In fact, we could say that x of x is just x. We can think of this as the identity function. So what can we do with this equation? Let's differentiate both sides with respect to x. So on the left, we get the derivative with respect to x of this function. On the other side, the derivative with respect to x of a constant is 0. Now, on this derivative, we can use the chain rule that we just saw up here. So this is going to be the partial derivative of f with respect to x times the derivative of x with respect to x, plus the partial of f with respect to y times the derivative of y with respect to x. So this derivative by the chain rule equals this stuff. And then on the other side of the equation, we just have equals 0 as we did up here. Now, the derivative of x with respect to x is just 1. So this term is this partial derivative times 1. And so we can rewrite this equation just as the partial of f with respect to x plus the partial of f with respect to y times the derivative of y with respect to x equals 0. Let's suppose we have a function which we'll call capital F, and it satisfies the following equation. Capital F of x comma y equals c. So f here is a function of two variables, and the two variables we're using are x and y. C is a constant. So let's suppose that this defines y as a function of x implicitly. Then what equation does y satisfy? Well, let's differentiate both sides of this equation with respect to x and see what happens. To differentiate this with respect to x, we have to use the chain rule, and that's going to be the partial derivative of f with respect to x times the derivative of x with respect to x, plus the partial derivative of f with respect to y times the derivative of y with respect to x equals 0. Now, we notice that the derivative of x with respect to x is 1, so we just have this partial derivative here times 1. So that term simplifies to the partial derivative of f with respect to x. This one we'll just copy down here. And on the other side, when you differentiate constant with respect to x, you just get 0. Derivative of a constant is 0. Now, if we look at this, this is a differential equation kind of in the form that we saw before, but for some reason, probably historical, people, instead of writing the differential equation this way, would multiply both sides through by dx. And if you do that, you get the partial of f with respect to x times dx plus the partial of f with respect to y times dy equals 0. So when people talk about exact equations, they usually put the equation in this form and then ask themselves or others is this equation exact or not? So now let's get a definition of an exact equation. Consider the ordinary differential equation m of xy times dx plus n of xy times dy equals 0. And let's ask the question, can we find a function capital F of xy such that the above equation is the partial derivative of f with respect to x dx plus the partial derivative of f with respect to y dy equals 0. In other words, is there a function f such that the partial of f with respect to x equals m up here, and the partial of f with respect to y equals n up here? If the answer to that is yes, then we say that ordinary differential equation that we have up here is exact, and the general solution of the ordinary differential equation is f of xy equals c. The graphs of this equation for various values of c are called the integral curves for this differential equation. So let's suppose we have this ordinary differential equation. How can we tell if it's exact? And if it is, how do we find capital F of xy such that the partial of f with respect to x equals m and the partial derivative of f with respect to y equals n? Okay, well, if we did have a function f of xy such that the partial of derivative of f with respect to x equaled m and the partial derivative of f with respect to y equaled n, then we could say the following. Let's take this first equation and differentiate both sides of this with respect to y. So if I differentiate this with respect to y, we get the second partial derivative of f with respect to y and x. If we differentiate this right-hand side with respect to y, we just get the partial derivative of m with respect to y. Now, what happens on the second equation if we differentiate both sides with respect to x? On the left-hand side, we'll get the second derivative of f with respect to x and y, and on the right-hand side, we'll get the partial derivative of n with respect to x. Now, assuming that these two second-order derivatives are continuous, then we know that this equals this by Clairaut's theorem. And so that must mean that the partial of m with respect to y equals the partial of n with respect to x. So assuming that those partials are continuous, we get this result. The partial derivative of m with respect to y has to equal the partial derivative of n with respect to x if we have an example. There is a converse to the result that we just talked about. If there's a rectangular region R in the plane such that the partial of m with respect to y and the partial derivative of n with respect to x are continuous inside R, and if those two are equal inside R, then there is a function capital F of xy such that the partial derivative of f with respect to x equals m of xy, and the partial of f with respect to y equals n of xy. In this case, the ordinary differential equation that we have here is exact. So basically, this is our test for an exact equation. Are these two partial derivatives continuous? And do those two partial derivatives, are they equal? Notice we're differentiating m with respect to y. We're differentiating n here with respect to x. So let's talk about solving the exact equation. How do we find the function capital F satisfying these two conditions? f would have to satisfy these conditions if we already know the equation is exact. And the answer, more or less, is here I have the derivative of a function equals another function. Why not just integrate both sides to find out what f is? So we're going to more or less use what we could call partial integration. As far as I know, no exact terminology has been found for this, and no notation is used. We just have to remember what we're doing. So if we have the partial derivative of f with respect to x equals m of xy, that means that capital F of xy has to be the integral of m of xy dx. And when we're evaluating this integral, we're integrating with respect to x, treating y as a constant. So we're kind of undoing the partial derivative where we treated y like a constant. Now we're doing anti-differentiation where y is treated like a constant. Okay, so y will be treated as a constant when we integrate, and the arbitrary constant of integration that we tack on at the end will be an arbitrary function of y. And the reason we can do that is if we differentiate that with respect to x, the derivative of h of y with respect to x is going to be 0, and so everything works out nicely. But then we have this second equation to worry about, and what we will do is to find that function h of y that satisfies this second equation. So the technique is to integrate this first equation, and you'll get a function h of y as an arbitrary, more or less, function of y, and then use that to make your function also satisfy this second condition. As an example, let's consider this problem. Let's look at 2x cosine y dx minus x squared sine y dy equals 0. Notice in these equations we're considering, we always have equals 0 on the right-hand side. Let's determine if it is exact. Okay, so we'll think of this as m of x. We'll think of this stuff as n of x. So the first thing I'll do is look at the partial derivative of m with respect to y. So that's the partial derivative with respect to y of 2x cosine y, and that is minus 2x times sine y, since the derivative of cosine y is minus the sine of y. Also, the partial of n with respect to x is the partial derivative with respect to x of minus x squared sine y. Okay, and here we're treating, when we differentiate this with respect to x, we're treating sine y as just a constant. And so what we have is this constant sine y times the derivative with respect to x of minus x squared, which is minus 2x. Now, if we look at these two, they're equal, aren't they? So the partial of m with respect to y and the partial derivative of n with respect to x are equal. And also, these are functions that are obviously continuous everywhere for any values of x comma y in the plane. So we have that these partials are continuous. We have that these partial derivatives are equal everywhere. And so our ordinary differential equation is exact basically everywhere in the plane. So now let's solve this exact differential equation. We can think of this as m of xy times dx plus n of xy dy equals 0. Notice when we're considering these types of differential equations, we always have equals 0 on the right-hand side. Okay, so since we know it's exact, we know that a capital F exists that satisfies certain conditions. One of the conditions it has to satisfy is the partial of derivative of f with respect to x equals 2x cosine y, which is what we have here. Integrate both sides with respect to x. On the left-hand side, the integral of this with respect to x is just f. On the other side, we just have the integral of that stuff dx. Now, when we integrate this, we're doing what we can think of as partial integration, where we're treating y like a constant. So if we integrate a constant times 2x, we get that constant times x squared, plus an arbitrary constant. But from what we saw before, this is going to be an arbitrary function of y. We can add anything here, and it'll still satisfy this equation, because when we differentiate this thing with respect to x, we'll just get 0. So from this equation up here, we have this is f, and then if we differentiate it with respect to y, we'll get the partial derivative of f with respect to y equals minus x squared sine y plus h prime of y. Why did we calculate this? Because we also know that the partial of f with respect to y has to equal the n of xy that we have here. So it has to be minus x squared sine y. So compare what we have for this partial derivative here. Compare what we have here for that same partial derivative. And we notice that this part here is the same as this part here. So this h prime of y in this case is going to have to be 0. And so we have to solve this equation for some h that satisfies it. Well, h of y equals a constant would satisfy this equation, and I decide to pick a particular constant that's easy. How about h of y equals 0? And that means that our f of xy function is just going to be x squared cosine y. I got that from over here. F is x squared cosine y plus 0. And our general solution then is f of xy equals an arbitrary constant. So we get a family of curves here. Those curves are sometimes called integral curves for this differential equation. As another example, let's solve this equation if we can. 2xy cubed dx plus the quantity 3x squared y squared minus 6y dy equals 0. First, we'll check to see if this is exact, and if it is exact, then we need to find a function capital F such that this is the partial of f with respect to x dx plus the partial of f with respect to y dy equals 0. So first of all, let's think of this stuff as m of xy. Think of this stuff here as n of xy. So the partial of m with respect to y equals the partial derivative with respect to y of 2xy cubed, and that is 6xy squared. The partial of n with respect to x is the partial with respect to x of this stuff, and partial derivative with respect to x of this term is 6xy squared. The partial derivative with respect to x of this term, which doesn't involve x at all, is 0. So partial of n with respect to x equals 6xy squared. These two partial derivatives are equal, so the equation is exact. So we now want to find a function f of xy such that this term right here, this factor, is the partial of f with respect to x, and this factor here in the second term is the partial of f with respect to y. So we let the partial of f with respect to x equal 2xy cubed. Integrate this with respect to x, treating y as a constant. So f of xy is the integral of 2xy cubed dx, which is x squared y cubed, plus an arbitrary function of y. We can add this to it, we must add this to it, this term, because the partial derivative of this with respect to x is 0. And so no matter what function of y we have here, this function right here, these two terms, will satisfy this equation up here. So then the partial of f with respect to y, excuse me, let's get that by differentiating this stuff right here with respect to y. This is f, remember, and so we'll just differentiate it with respect to y. So the partial with respect to y of x squared y cubed plus phi of y, differentiate this term by term, and we get 3x squared y squared plus phi prime of y. So that means that phi prime of y, comparing it to what we have up here, has to be this minus 6y. And so phi of y by integration is minus 3y squared. So the solutions to this differential equation then are going to be x squared y cubed minus 3y squared equals a constant. Basically, f of xy equals c. Hello, this is an addendum to lesson 6, an example of solving an exact ordinary differential equation with an initial condition. I'm Ronald Johns. So let's consider a problem containing a side condition. Let's look at this problem. This stuff times dx plus this stuff times dy equals 0. That's a differential equation. Hopefully it's exact. And we also want y of x to satisfy y of pi over 2 equals 0. So differential equation, first order differential equation actually, plus this initial condition, solve for y of x. First we'll show that the ordinary differential equation is exact and find the implicit solutions f of xy equals c. There could be lots of solutions over here depending on the value of c. Then find the particular implicit solution f of xy equals c naught, whose graph contains the point pi over 2 comma 0. So we have an implicit solution, perhaps this curve, turns out not to be this curve or look like it, but we have a curve defined implicitly, and that curve goes through the point pi over 2 comma 0. Okay, here's the exact differential equation that we're considering. This is m of xy, and over here this stuff is n of xy. So look at the partial of m with respect to y first, and we'll show that that is equal to the partial derivative of n with respect to x. So the partial of m with respect to y is the partial derivative with respect to y of this stuff. The partial with respect to y of y minus 2 sine 2x. The partial derivative with respect to y of y is 1. The partial derivative with respect to y of minus 2 sine 2x is 0. And so partial of m with respect to y equals 1. Similarly, let's consider n of xy, which is x plus 15y squared, and let's differentiate that with respect to x. The derivative with respect to x of x plus 15y squared is 1 plus 0, which is 1. So these two partial derivatives are equal. These are continuous functions that we're looking at in a region, so the differential equation is exact. So let's solve that exact differential equation. We're trying to find a function f of xy such that the partial of f with respect to x equals m, and the partial of f with respect to y equals n. So let's start with the first condition on m. If we want the partial of f with respect to x to equal m, which is y minus 2 sine 2x, let's integrate both sides of this equation with respect to x. So f of xy then is the integral of y minus 2 sine x dx. Remember, we're treating y as a constant when we integrate because we treated y as a constant up here when we differentiated. So the integral of y with respect to x is xy. The integral of minus 2 sine 2x with respect to x is cosine 2x. And our arbitrary constant in this case can be an arbitrary function of y. If you differentiate this term by term, you will get what we have up here. Because if we differentiate this term with respect to x, the derivative of a function of y with respect to x is 0. And so what we just get is the derivative of this is y, the derivative of this is minus sine 2x, and the derivative with respect to x of h of y is 0. So far we have that f of xy has to be of the form x times y plus cosine 2x plus some function of y. If we differentiate this equation with respect to y, the derivative with respect to y of x times y is x. The derivative with respect to y of cosine of 2x is 0. The derivative with respect to y of h of y is h prime of y. So the partial of f with respect to y equals x plus h prime of y. But let's remember that this equation is exact, so we must have also that the partial of f with respect to y is equal to that function n of xy. And that, let's remember, was x plus 15y squared. So comparing these two expressions, both for the same partial derivative of f with respect to y, they both have terms of x, so h prime of y up here must equal 15y squared. That's what we have right here. So then anti-differentiate this with respect to y, and we have h of y is 5y cubed. Remember, that's going to be 15 times 1/3 y cubed, which is 5y cubed. So now we know what h of y has to be, so we can plug it back into our expression here for the function f of xy. F of xy is x times y plus cosine of 2x plus 5y cubed. So since the general solution to the differential equation is capital F of xy equals an arbitrary constant, we just have that this stuff, which we have down here, equals an arbitrary constant. No matter what constant we pick, we get an implicit solution. Actually, we might not if it turns out to be an equation that has no points in its graph. So far we have that f of xy is x times y plus cosine of 2x plus 5y cubed, and the implicit solution to the differential equation is f of xy equals a constant. We want to find a solution curve that goes through the point pi over 2 comma 0. This is going to have the form, this curve, the equation of it is going to be f of xy equals some constant c naught, and we want to find the c naught. This curve could go all over the place and not be the curve of a function. It might not pass the vertical line test, but hopefully a small piece of it at least would, and we can think of that curve then, that part of the implicit solution curve, as representing some function y of x. So we want a solution curve that goes through this point, which means that capital F of pi over 2 comma 0 has to be c naught. So plugging pi over 2 in for x and 0 in for y into this expression up here, we have pi over 2 times 0 plus cosine 2 times pi over 2 plus 5 times 0 cubed has to equal c naught. So if we add all of this up, we have a 0 term, cosine of pi is minus 1, another term which is 0. So we have 0 minus 1 plus 0 equals C naught. So the C naught has to be minus 1. So in that case, the particular implicit solution to our combined problem with that extra condition is x times y plus cosine 2x plus 5y cubed equals minus 1. Let us use SageMath to plot this equation. X times y plus cosine 2x plus 5y cubed equals minus 1. Let's write this as a function of x and y equals 0. We can do that by adding 1 to both sides of this equation. So this equation is equivalent to xy plus cosine 2x plus 5y cubed plus 1 equals 0. We can graph this equation in SageMath by using the function implicit plot. So let's see how we would do that. First of all, I would have to declare two variables. X and y are the variables which we will call x and y. I'll define g of xy to be this stuff up here. This stuff plus 1, just as we had here. Then implicit plot, and then inside parentheses, g of xy, comma, x goes from minus 5 to 5, comma, y goes from minus 5 to 5, and an end parentheses around the whole thing. This implicit plot command is going to sketch the graph of g of xy equals 0, which is equivalent to this equation up here, which is equivalent to this equation up here. When we do this plot, we get this graph, the part in blue. I've added a couple red lines here, one vertical, one horizontal, so that we can see that at x equals pi over 2, pi over 2 is just a little bit bigger than 3/2, and that's between 0 and 2, right about here. And drawing a horizontal line at 0, we have this. And so right here is the point pi over 2, comma 0, which our graph does intersect. Here we have a SageMath very short program written in a Jupyter notebook, one cell of a Jupyter notebook. In the first command, we just declare x and y to be variables with the names x and y. Then we define a function, g of xy equals x times y plus cosine of 2 times x plus 5 times y cubed plus 1. And then we have an implicit plot command here. We're going to plot g of xy equals 0. Here's the function g of xy. We're going to plot that thing equaling 0, where x will go from minus 5 to 5, and y will also go from minus 5 to 5. So I'll come over here, and I'll hit Shift-Enter, and we'll wait for the output. And there it is. Let's use the function f of xy equals x times y plus cosine 2x plus 5y cubed plus 3 to make an exact equation. Exact equation will look like this. So for this function, we'll compute the partial of f with respect to x, and it turns out to be this stuff here. Also, we need to compute the partial of f with respect to y. When we do the calculation, we get this stuff here. So we'll choose the differential equation to be the partial of f with respect to x, which is this stuff, times dx, plus the partial of f with respect to y, which is this stuff, times dy, equals 0. So for this equation, We know that it's exact because we made it of this form for this particular f, and thus we know that the solutions are the form f of xy equals a constant. For every value of this constant, we will get a solution to this exact ordinary differential equation. So next, I decided to add a side condition that our solution would have to satisfy, and I decided that I want the solution to be a function that goes through pi over 2 comma 0. In other words, I want the graph of this to go through this point as we have here. I guess you can say here's the point pi over 2 comma 0. Here's one of the implicit solutions going through that point. So in other words, if I have f of xy equals c, I have this stuff, which is f of xy equals c, and I want pi over 2 comma 0 to be a solution to this equation. That will allow us to find c. So we'll plug x equals pi over 2, y equals 0 into this side, and we have pi over 2 times 0 plus cosine 2 times pi over 2 plus 5 times 0 cubed plus 3 equals c. This term is 0. Cosine of pi is minus 1. 5 times 0 cubed is 0. Plus 3 equals c. So we have minus 1 plus 3 equals c. So c has to equal 2. So x squared, y squared, going back to this equation right here now, just letting the c be 2. X squared, y squared plus cosine 2x plus 5y squared plus 3 equals 2 satisfies that extra condition. And then by subtracting 3 from both sides of this equation, we can write it as these three terms from up here equal 2 minus 3, which is minus 1. I would like to thank you for watching this video. I hope you have found it to be an enjoyable learning experience. If you're interested in ordinary differential equations, there are additional videos in this series covering most of the topics in an introductory course in ODEs. Have a good day.